Okay, so we will revise once again the types of stresses. Number one, the very first category of stress, that is tensile stress. Tensile stress, when a body is subjected to equal and opposite axial pull forces, then stress produced in the body is called tensile stress. Tensile stress, when a body is subjected to equal and opposite axial pull forces, then stress produced in the body is called tensile stress. The diagram for tensile stress: if suppose this axial load is W and the cross-sectional dimension of this rod is a circle and the area of this circle is capital letter A, the diameter of this circle is small letter d, then the tensile stress produced in the area will be W upon A. In our case, it will be W upon pi by 4 d square. If the cross section is circular or square or rectangle, then according to the formula of the area, we will consider that area over here, the load will be capital letter W. So this is the tensile stress. When a body is subjected to equal and opposite axial forces, then stress produced in the body is called tensile stress. I have taken an example for a rod having cross-sectional dimension as circle. Then the tensile stress produced in the rod will be W upon A, that will be W upon pi by 4 d square. Number 2 is compressive stress. Compressive stress, when a body is subjected to equal and opposite axial push forces, then the stress produced in the body is called compressive stress. The direction of these two will change. Compressive. Then the compressive stress produced in the body will be sigma c W upon A is equal to W upon pi by 4 d square. We are taking this formula as pi by 4 d square because we have considered the cross-sectional area as a circle if the rod is circular. So compressive stress, the tensile and the compressive both are axial, both are because of the axial type of loading. So compressive stress, when a body is subjected to equal and opposite axial push forces, then stress produced in the body is called compressive stress. The formula. Okay, now we'll go to the third type of stress is bending stress. We represent it by sigma b. Bending stress is nothing but the combination of tensile as well as compressive. When a body is subjected to bending movement, when a body is subjected to bending movement, when the body is subjected to bending movement, we represent the bending movement by capital letter M. Then stress induced in the body is called bending stress. In the subject of strength of material, we have learned the formula, the direct formula for bending moment for different 4 cases. I'll draw a very simple case from there. If the beam is simply supported like this, and if there is a central load acting, capital letter W, then the bending moment induced into the body because of this capital letter W, if it is capital letter M, then sigma B bending stress will be M upon I into Y max. Now what is M, what is I, and what is Y max? Suppose if the cross section of this rod is a rectangle, then the central layer of this beam will be called the neutral axis of the beam. We represent it by NA, neutral axis. Then capital letter I is moment of inertia of this cross section about neutral axis. So capital letter I. Y max is the distance of extremmost layer from the neutral axis. So in our case this will become Y max. Y max. Capital letter I is moment of inertia of cross section about neutral axis. So I max is this. Capital letter M is maximum bending moment acting at the beam. Okay, you have to revise all 4 formulas of maximum bending moment. We write it by M max also from the SOM for simply supported beam with one central point load, for simply supported beam with UDL, then cantilever beam with one point load at free end, and fourth case is cantilever beam with a UDL over the entire span. You can revise these 4 formulas for M max from strength of material textbook. Okay, so what is bending stress? When a body is subjected to bending movement, capital letter M, then stress induced in the body is called bending stress. In bending, the material is simultaneously under the action of tension as well as in compression. In this case, the beam is going to bend in the sagging nature, so the layers above the neutral axis will be in the compressive stress, and the layers below the neutral axis will be under the tensile stress. This is bending stress. Now we will go to the next category, that is transverse shear stress. Number 4, transverse shear stress. We generally represent by tau, the shear stress. When a section is subjected to equal and opposite forces, tangentially, then stress induced is shear stress. In previous lecture, I have given you the 3 categories of shear stress. One is single shear, second is double shear, and third is punching shear. Single shear, double shear, and punching shear. If I will draw the diagram for the same, you can easily remember. If two plates are joined with the help of a rivet and the load is acting tangentially like this load is tangential for the rivet. Double shear, or here only one plane is going to shear, that's why it is called single. If 3 plates are attached with the help of a rivet, then this rivet may fail at 2 planes, that's why it is called double shear. Punching shear, if you want to punch a hole into a plate having thickness T, and if the diameter of this hole is small letter d, then the area which is going to be punched in this case is under the action of punching shear. I have given you the formula for all these 3. If the rivet is circular in nature, here this rivet and the punch, the drill is in circular shape, then the shear stress induced in single shear will be tau is equal to capital letter W divided by pi by 4 d square. Only one plane is going to shear. I'll draw that shearing plane with this red mark. This is the plane which is going to shear. You can imagine very well. Now, the shear stress induced in double shear will be capital letter W divided by 2 into pi by 4 d square. Here, 2 planes are under the action of shearing. One is this and the second one is this. And in punching shear, the area under the shearing action is this cylinder which is going to punch. The thickness, the height for this cylinder will be equal to the thickness of the plate, and the diameter of this cylinder is small letter d. So area under action of punching will be W upon pi into d into t. So this is the formula for punching shear. I expect that all of you have understood the transverse shear, all the types of the transverse shear, that is single shear, double shear and punching shear. For attempting the numericals, all these formulas are very important. Now we'll see the next category, that is crushing stress. Number fifth one is crushing stress. Crushing stress, it is localized compressive stress induced at the surface of contact. It is localized compressive stress induced at the surface of contact between two components of machine. Which are, this is important, which are relatively at rest. So what is crushing stress? This is new for you because in some we have not covered the crushing stress. We represent this by sigma Ck. Localized compressive stress induced at the surface of contact between two components of machine which are relatively at rest. We'll again take the example of the two plates which are joined with the help of a rivet. Now let the thickness of plate, both the plates are small letter t, and the diameter of this rivet is small letter d. Okay, so what is crushing stress? You are aware that at this plane the shearing is going to happen. But what is crushing? See, this concentrate on these lines. This is the part, this is the plane of the rivet which is in contact, continuously in contact with the plate. Okay, so this is the plane which is, you can consider as common plane for the plate as well as for the rivet. Okay, so in crushing stress, we consider this area, the projected area of this the area in connection is cylindrical, but when we will draw its projection, it will be look like a rectangle having width as diameter of the rivet and height as the thickness of the plate. So the projected area which is under crushing is d into t. So projected area. Projected area of rivet and plate, because these two components are in contact and they are at rest, they are not in motion. So projected area of rivet and plate will be d into t. So what is crushing stress? This crushing is because of this load W, means this crushing stress sigma Ck in this case will be equal to load upon the projected area which is under crush. So d into t. This will be W upon d into t. So for this plate and rivet, it is crushing stress induced will be W upon d into t. For the lower half, it will also same. So what is crushing stress? The localized compressive stress induced at the surface of contact between two components of machine which are relatively at rest. And area involved in crushing is always the projected area of those two matting parts. दोनों का जो common plane area रहेगा, that projected area will be considered under crushing. Now we'll see the next category, sixth one is bearing stress. Bearing stress, it is also called bearing pressure, and it is always represented by PB. It is very similar to the crushing stress, but only difference is the parts will be in a relative motion. Okay, so what is bearing stress? It is a localized compressive stress induced at the surface of contact between two components of machine which have relative motion, which have relative motion. Sometimes the bearing and the support, bearing and the shaft are in relative motion, so that will be considered under bearing pressure. Okay. I'll draw the diagram for bearing stress or bearing pressure. If suppose this is the shaft, this is supported under this bearing. You are aware that crankshaft, the different shafts are supported with the help of bearing. Now, if the load, the vertical load coming on the bearing is capital letter W, then the area under bearing stress will be the common area between the bearing and the shaft, and not actually the common area, the projected area of that common area. So this plane is under bearing, so I am drawing that by red, the projected area of this much, that will be a rectangle only. So suppose if the length of the bearing is small letter L and the diameter of the shaft is small letter D, then the projected area and the common area which is under the bearing will be A is equal to D into L. We are not going to take the cylindrical area of the shaft, we are going to take the projected area, because in crushing and in bearing the area considered is projected area. So see, this bearing pressure or bearing stress will be equal to W upon the area under bearing, that is D into L. So the formula for bearing stress or bearing pressure will become like this. What is bearing stress? Localized compressive stress induced at the surface of contact between two components of machine which have relative motion. They will have relative motion. So the shaft supported in the bearing is a very good example for the bearing stress. I expect that you all have understood all these 6 categories of the stress. There are much more, but when we will take it when we have the numericals on that. Okay, so this is the theory part. Now I'll continue with the numerical part in my next part of this lecture.